So what you may have noticed when you're running these comparisons is that the answer you get for dissolved volatiles is actually quite different between the different solubility models. And we can show this in more detail by taking a specific melt composition. So this is a morb with 47.4 weight % silica. And then we're basically calculating dissolved volatiles for lots of different pressures for lots of different models, and we can plot them up. And what we can see is that at sort of less than 2 kilobars, Shishkina, Icona, Marziano and Magmasat are all very, very similar. And then at higher pressures, they begin to diverge. And what we see is that kind of at all pressures, volatile calc basalt and perpale plot to much higher CO2 contents. We can draw the same diagrams for water and all the same colours, except we've now added more because this is only a water model. And what you can see is that while pretty much all of the models lie outside the error range of Magmasat for CO2, for water, other than Icona, Marziano and perpale, they all pretty much lie within that error window. And this is something we see when we look at a broad range of melt compositions. In general, CO2 solubility is very, very different between models, whereas water solubility is more similar. So as a very first pass, when you start looking at a new volcanic system, it can be really helpful to plot these kind of diagrams to work out if you're looking at a very CO2 rich system and you see something like this, you're probably going to need to put a lot of effort into choosing your model because the number that you get out is going to be highly dependent on that choice. Whereas if all of your model lines are really, really similar, it's actually not going to make that much difference which model you've chosen. So now I'm going to talk about how you can look at interrogating the different model results and why they give different answers, specifically using volatile calc basalt. So if we remember, the Dixon simplification used the North Arch lavas and it used the strong trend between pi and silica content in these lavas. And this resulted in this constant for the amount of carbonate being expressed purely in terms of melt silica content. And what this basically assumes is that your samples, which you're feeding SiO2 in for, follow the same pi-silica relationship as the North Arch glasses. Now, the more observant of you will notice as silica goes above a certain value, this number would actually become negative, and that would result in you having a negative carbonate ion solubility. That isn't ideal. You do not get negative CO2 solubility. So what volatile calc basalt does is if you try and enter a silica content more than 49, it will tell you you're not allowed to do that. And what most people have done at that point is just enter 49, even if say their melt inclusion is 52 or 50 weight % silica. And that's fine, but at that point what you're saying is that you're assuming all of your melts with more than 49 weight % silica have equivalent pi values to sort of 0.4, which is what the North Arch trend is at that silica value. So let's look at some examples. Say you have a melt, which is this red composition. This lies very well on the pi silica line, so volatile calc basalt is probably going to do a reasonably good job. Similarly, if your melt is down here, again, silica is being a good proxy for pi. In contrast, if your melt lies over here, firstly, it has a pi value of about 0.7. Yet, using the volatile calc relationship, you're assuming that it has a pi of about 0.4. And this means you're pretty going to get its CO2 solubility wrong because its CO2 solubility is probably far higher than volatile calc is going to predict. In contrast, if you're down over here, at a given silica content, your melt has a much lower pi value than the North Arch lavas, so a much lower CO2 solubility. And if we plot that morb 2 composition on, we can see it lies below this line. So basically, volatile calc basalt is projecting it up to this line effectively and saying based on its silica content, we predict a high pi value and therefore we predict a high CO2 solubility. So now we're going to go to the example of doing batch calculations, and we're going to be comparing models using some melt inclusions from Mike Cassidy and also introduce some isobars.